Is that just like a computer thing?
What do you mean?
Create a simulation on a computer?
Yeah, Monte Carlo technique, they call it. So let me fill you in on probability. There's three, there's three basic ways of designating probability. Assigning probability. The first one, we really don't use a lot. It's called subjective. It's like you say to somebody, what do you think the football team's chance of winning today is? I don't know, 50-50. That's subjective probability. What do you think the chance of it raining tonight? It's subjective. It's just something that well, it's been raining the last 3 nights. I don't know. 1 chance in 4. I don't know, but you give it a numerical treatment. There's 2 others. One is called theoretical. Or classical. We analyze the situation. Like if I said, what's the probability of flipping a head if I flip a coin? What would you say? 1 out of 2. Because there's 2 outcomes, head or tails. So unless, barring the fact that the coin's been altered in some way. So we would say, given a fair coin, untreated, classically we would do 50-50. In classical terminology, it's always equally likely outcomes. Like if I roll a die, there's 6 sides. So each side is equally likely. So the probability of any particular side would be 1 chance out of 6. That's how we would assign it. So all outcomes are equally likely. That's classical or theoretical. You were theorizing. Now, we can update that given the history of what happens. Like if I flip a coin 10 times in a row and it comes up 10 heads, well, it's going to lead me to think something's wrong with the coin. But if I can't, if somebody tells me no, it's a fair coin, then the probability on the next toss is still 50-50. Because if I toss a coin 100,000 times in a row, there's going to be a sequence where I'm going to get 10 heads in a row. It's not out of the question. It's not improbable. So the other way of talking about probability is empirical. Empirical means measured. So theoretical and empirical are the two mechanisms we use. And empirical is just the relative frequency. If I'm a basketball player and I've made 20 out of 30 free throws, then that's a relative frequency 67%, 0.67. Right? So that would be the probability that I would make the next free throw would be 0.67 based on the empirical. So when we assign probabilities, we assign them to procedures, processes. For lack of a better term, we call them experiments. We call flipping a coin an experiment. And for an experiment, the set of all simple outcomes called the sample space. It's a set of all simple outcomes. So for a coin, you would say S or SS, let's say heads, tails. So these are simple outcomes. We usually use capital letters. For a die, singular of dice is die. The sample space would be the numbers 1, 2, 3, 4, 5, 6. So that's the set of simple outcomes. Simple outcomes meaning they stand alone. They don't
Interfere with them.
they're separate. It's only one possibility. But if we have more than one possibility, like if I were to say, what's the event of rolling an even? Then that would be 2, 4, 6. That would be an event would be a subset. So an event is a subset of S. And we use capital letters for events. So for a die, E would be the set of 2, 4, 6. That would be a subset. This is a subset of this, so it's the event of evens. You notice it has 3 simple outcomes. So an event doesn't necessarily have to be one single outcome, although it could be. You can have an event with a single outcome or multiple outcomes. It all depends on how you're describing the experiment or the process or the procedure that's being investigated. So the notations, an event we'll call A, we say A is the event. The notation for probability, we say the probability of event A is written P of A. Probability of event A. Like a function from algebra. And the probability of any event has to be between 0 and 1. Now it could be as a decimal or as a percent. If you use percent, then it's 100%. So every probability is a number between 0 and 1. Every probability that we use. You can use fractions, decimals, percents. They're interchangeable. For us, we're going to probably use mostly decimals or fractions. So we would say the probability of a head is 1/2 or 0.5. The probability of a 3 when you're rolling a die would be 1/6. So probabilities have to always be between 0 and 1. The event A bar, or I'll put in parentheses, A prime, there's different ways that authors notate. It's called the complement. So it could be written like those. The event, I think this book uses A bar, is the complement. Of A. And A and A bar are mutually exclusive. So their union is all of S. Their intersection is empty. Which means that the probability of A plus the probability of A bar is equal to 1. Because all the outcomes that are in A are not in A bar, and vice versa, but combined, they equal all of S. So the probability of S is always equal to 1. Total probability is always 100%. And the probability of the empty set is 0. Like, logically, if I said I flipped a coin, there's only 2 outcomes, right? But there's actually a third. It's highly improbable, but it's not impossible. Now, this is the honest truth. I was in a statistics class like this at a university in Ohio, and I had a large desk in front of the class, and I went like that. And the coin stopped like this. And I looked up, and we all looked at it. We could count to almost 12 seconds. It's like, everybody looked around, and then it fell over. But it just reminded everybody that it's not impossible. And that's probability 0. Now, it doesn't mean that something's not going to happen. It just means that it's highly, highly unlikely. Like the sun not coming up in the morning is probability 0. And I always like to say, because if it doesn't, we won't know about it. Do you catch my drift? It's kind of like when you have a deck of cards. You guys know how deck of cards? How many in a? It's called a bridge deck or a poker deck. 52. You know cards? Not at all. There's going to be some examples of cards. 52 cards. 4 suits: spades, hearts, diamonds, clubs. There's 13 kinds of cards. Ace, king, queen, jack, and then 2 through 10. The ace in some games can be a 1 or it can be a high card. But there's 13 kinds. So 4 suits, 13 kinds, 52 cards. So what's the probability of if I deal out 5 cards? What's the probability of getting 5 aces? 0, because there's only 4 of them. So that would be. I mean, see, you could say it's impossible, but if you were playing with somebody that was a cheater and they did it, it happened.
So probability.
But the probability of it happening, naturally occurring, is 0. Whether you want to call it impossible or highly, highly improbable, either way, it's probability 0. Notice that you can algebraically, you can solve for either one of these. The probability of complement is 1 minus the probability of the event. So either way, you can put them either way. So they're complementary. They don't overlap, but they're complementary. That's what it means for complementary. They constitute the whole sample space. Like evens and odds. They don't overlap, but there's 3 evens and 3 odds. They don't share any outcomes, but they make up the whole sample space. The odds would be 1, 3, 5. So they're disjoint. We call that disjoint. If they don't overlap, we call that disjoint. So those are some of the notes. And then we'll add some other stuff here as we go. So that's a good start. Any questions so far? Yeah. No? All right, I'm going to go ahead and do application screen. And we're going to go to the study plan, start right here. So some things will jump out very quick. Okay, so here's the complement. What does A bar denote? It denotes the complement, meaning that A bar consists of all outcomes in which event A does not occur. Make sense? Okay. That's because they're disjoint. So if the probability of A is 0.006, what's the probability of A bar? Who's paying attention? Total probability is?
1.
So they have to add up to? So what's the number I got to put in there?
I can't do the mental math on that one.
Subtract 6 from 1,000.
Be
994. Both those two add to 1,000?
Yeah.
All right. So a weather forecasting website indicates that there's a 15% chance of rain in a certain region. Now, there's a lot of subjective probability in weather forecasting, obviously. They got all kind of maps and whatever, but radar screens, but they have to make it subjective. Well, so what is this, when you hear this, what does that mean to you? What it means is that in a given area, there's a 15% chance that it will rain somewhere at some time. That's what it means. Doesn't mean everywhere for 15% of the day. Doesn't mean for 15% of the area. It just means that it's somewhere during that region, there's a 15% probability that it'll rain. That's how you read that. Okay? In case you never realized that. All right, so which one of these cannot be probabilities? A. Is A a possible probability? How about B?
No.
Probabilities are never negative. C.
Yes.
D.
No, because it's over 1.
E.
No, because it's over 1.
F.
Yes.
G.
Yes.
H.
No, square root of 2, which is 1, so yes.
1.14.
So then they can't.
Square root of 1 is 1. Square root of 2 is it's larger than 1.
Yeah, so you might be.
Yeah, it says which ones cannot be.
Oh, yeah, okay.
Yeah,
Never mind.
it says cannot. It's highlighted too. I blew it this morning. All right, so everybody understand what's going on there?
Yeah.
We picked the ones that cannot be. See, all the other ones are between 0 and 1, inclusive. We can include 0 and 1. They're okay. All right. 17 of 100 digital video recorders in an inventory are known to be defective. So what's the probability that a randomly selected video recorder is defective?
It's 17 out of 100.
So how would you write that?
0.17.
0.17, good. You agree, Terry? 17 out of 100, that's the decimal. That's an example of the relative frequency.
Okay.
Relative frequency, the way we write that would be, we would say the number in A divided by the number in S. That's the probability of A. That's the relative frequency. And in statistics, we say that if we choose an element from A, that's a success. If we don't, that's a failure. That's the statistically. If I'm looking for a head, if I roll a head, it's a success. If I roll a tail, it's a failure. If I'm looking for a 5 when I roll a die, a 5 would be a success. Any other number would be a failure. That's statistical lingo. So the probability of a success here, of picking a defective one, is 17 chances. The n means how many. That's the number, n. It's very similar to the sample size. This is a function just like probability. This is how many the number that are in A. So 17 defective divided by 100 total would give you 0.17. So these, you'll see these letters used in that fashion. Assume that 200 births are randomly selected and 5 are girls. Use subjective judgment because we're not really invested in the totality of this. Would the 5 be significantly low, significantly high, or neither one? significantly low. Why would you say that? What do we expect the number to be? 100. Because equally likely. Now, in reality, there's more girls than boys. It's 0.51 to 0.49. But for most practical purposes, we just say 50-50. It's just easier. So it's significantly low. Because if we expect 100, now, we would put a confidence interval around the 100, plus or minus 2 standard deviations. But we don't even know what the standard deviation is for this. I'll tell you what it is. It's square root of 50, which is about 7. So 2 times 7 is 14. So the 90% probability or confidence interval would be from 86 to 114. 5 is much less than 86. We're not anywhere near that. So, but see, that's numerically how we would do it.
So you said it's 0.51 for the girls born, or that you have a girl?
Yeah, in reality, it's a little bit bigger. In reality, there's more girls born than boys. Yeah, slightly higher than 50%. So 5 is based on the fact that we expect the number close to 100. Okay, here's another one. Now assume there's 1,900 and 957 are girls. Now what's half of 1,900?
9.5.
Yeah, 950. So 957, is that too far from 950 to be, will it be significantly high, significantly low, or neither? Neither one. Because we expect it to be close to 900. And it is. It's 957 is relatively close. I could tell you what the standard deviation would be the square root of 475, which is about 22. So 2 times 22 would be 44. So you're going to add 44 or subtract 44 from 950. So you're looking at anywhere between 900 and 1,000 would be a confidence interval we could live with. So 957 is well within that range. That's numerically how we would do it. But they didn't ask us to do that. They asked us to do it subjectively. Are we close enough to 50-50? Yes. That's what we're doing right now. I'm just giving you the numerical part of it in case you're interested. Okay, is it 13? No, wait a minute. Yeah, 14. Okay. Here, we might as well do this. It talks about odds. You guys know about odds, right? Odds. Let's see. Can I erase this? Erase. Odds come in 2 flavors. You got odds for and odds against. Odds for A. When I write here, I mean event A. It's just the probability of A divided by the probability of A bar. So it's the number of, actually, what happens is this will be NA over NS divided by NA bar over NS. Guess what? When you invert and multiply, these cancel. So it's the number of outcomes in favor of A divided by the number of outcomes against A. So I can go ahead and erase. You see what I did?
Yeah, sure.
Yeah. So guess what the odds against are? You just flip the fraction. You just flips the fraction. It's the probability of A bar divided by the probability of A. So it's the number of outcomes against A divided by the number of outcomes in favor of A. You just flip the fraction. See, we define it in terms of probability, but when we have fractions, the denominator, the denominator in the relative frequency fraction divides out. So this is when it says 27 to 29 to 71, when you add those up, you have 100, which is nice. That's the denominator. The denominator is always the sum of the odds. So there's 29 in favor of A and 71 not in favor of A. So they want to know the degree of likelihood. So it's 29 out of 100, 0.29. Yeah, that's right. It is. Because what this is essentially 29, this is 71, but they canceled out the 100, which is the denominator when you put it as a probability statement, right? Does that make sense?
Yeah.
All right. So here's another one. In a certain, but you got to be careful here. In a certain instant lottery game, the chances of a win are stated as 6 in 31, not 6 to. I'm sorry, 23. Not 6 to 23, but 6 in 23. That's a fraction. 6 is the number of outcomes in favor, and 23 is the total number of outcomes. So it's a relative frequency. So what I got to do is change it to a decimal. It says 3 decimal places. So I have a fraction, but I need a decimal. So that means I need to do a division. 6 divided by 23, and round it to 3 places. 0.261. 26% chance of winning the lottery if it's truly 6 and 23. The N, you see, tells you there's 6 chances in favor, 23 are the total number of chances. I don't know why they didn't say 6 out of 23. Maybe they're just trying to be slick. Yeah, so be careful there. That was 14. Okay, 15. In a certain study, the chance of encountering a car crash on the road is stated as 16%. Express the indicated degree of likelihood as a probability. Well, essentially, it is a probability. It's just as written as a percent instead of as a decimal. So how do I change that to a decimal? 0.16. See, when you see this, you could say 16% as a way to tell somebody, yeah, 16% chance. Because if you say 0.16, they're only you talking about. You know, in the lingo, 16% is how we say it. All right. Number 19. Is it impossible to get 10 kings when selecting cards from a shuffled deck?
No. 0.
It's impossible. Yes, it's impossible. So it's probability 0. You just said it backwards. We already kind of discussed that one. So. Is it impossible to get 5 aces when selecting cards from a shuffled deck? Yeah, we already discussed that. Okay, now we're getting into, yeah, let me see. All right, so this is what we call a 2x2 contingency table. There's 2 test results and 2 statements about whether the person lied or did not lie. So there's four possibilities. So it's 2x2, 2 rows, 2 columns. And so normally what we do is we get the what we call the marginals. So the marginals, so we got not lie and lie. Positive, negative. So 10, 42, 31. So how many are total positive? This is the marginal, 52. How many are negative? 38. So the grand total for the sample is 100 people. How many did not lie? 41. How many did lie? 49. Actually, that's 90. My bad. So, you know, if you add these two, you get 90. If you add these two, you get 90. This is the grand total for all of those four. But now you have marginals. You can take any of the four possible characteristics, and you can get a simple relative frequency. Because the question they're asking us here is, how many were not lying? Well, not lied, 41 out of 90. So I need a calculator again to get an exact decimal. 456. I assume it's 3 places. Yeah, they usually have 3 places. Okay? And then they're going to say, is the result close to the probability rounded to 3 decimal places of getting a negative result? Where do they get that? Well, the negative result is the second row, so that's 38 out of 90. And it's going to be pretty close, I think. See, that's where they got the 422. See it? Okay, so the question is, an absolute value of 5%, are they close? Yeah. If you add 5% to 42, you get 47. So yeah, yes, because there is less than a 5% absolute difference between the two answers. I'm not sure why they want us to do that, just to compare the two. You good? All they're saying is that these two are within 0.05 of each other. Right? Because if you subtract it, you get 0.034 or negative, whatever way you subtract it. They're within 0.034 of each other, which is less than 0.05. Okay. So there's that 5%. In this case, it's not 5% of the difference being 5% of one or the other. It's the absolute difference. You know, they stress absolute difference. So absolute difference means just how far apart are they? That was 24, 27. In a genetics experiment on peas, one sample of offspring contained 357 green peas and 127 yellow peas. This is like a takeoff on, you know, guys ever heard of Gregor Mendel? He was a monk. He lived in France or Portugal or something. He did genetic studies using peas and the color of it. Anyway, he's very famous. So he has 357 green and 127 yellow. Based on these results, estimate the probability of getting an offspring that is green. Well, don't forget now, the number that are green are 357, and the number in the sample space are the total, which is 357 plus 127. So the denominator is the total number of plants. So that's the relative frequency, right? Because the denominator represents the sample space, the numerator represents the number of successes. So it's 0.738. Pretty close to 3/4, right? 3/4 is 0.75. Is it close? Yes, it's reasonably close. Now, we're not going to stipulate here how statistically close it is, but just looking at it, you would say, yeah, it's reasonably close. Later on, we're going to actually form the confidence interval to show you that how close it really is. Okay? We good? All right. 27, 29. In a survey of consumers aged 12 years, here's a relative frequency. They want to know the probability of 4 or more cell phones. Well, the numerator is the number for 4 or more, which is the last number, 109. So that's the numerator. That's the number of successes. The total number in the sample space would be the sum of all of the respondents. So 204 answered none. 288 answered 1. 135 answered 3, and 109 answered 4 or more. Oop, I forgot 370. I got 204, 288, and then I skipped to 135. I forgot the 370. And then the 109 is the last. So the denominator, once again, is the whole sample space of all the people that answered none, 1, 2, 3, or 4 or more. So it's 5 categories. And they want to know the probability of being in the 5th category of 4 or more. So the possible number of successes is 109. So what they're saying is, what's the probability? Well, I got 109 successes out of the total sample space, would be 0.99099. Right? About 10%, roughly. Is it unlikely for a household to have 4 or more cell phones? And they give you the stipulation. Is 0.099 greater than that or less than that? It's greater, so it's not unlikely. So is it unlikely? No, because the probability is greater than 0.05. If it's less than that alpha, the significance level, then it's significant. That's what they're asking us, right? Is it unlikely? Unlikely would mean significant. They use that 5% rule a lot. Okay, now we're going to get into got 3 kids in the family. Those are all the possibilities. First one being the oldest, second one being the middle, and the third one being the youngest. That's 8 possibilities. Because there's 2 choices for each of 3 children, 2 cubed, 2 times 2 times 2. Can I erase this now? Okay, a nice way to do this is what we call probability trees. Whenever I get stuck, I just draw a tree. So the first child is the first one. Boy, girl. It's 50-50. Total probability, all the branches leading from this node have to add up to 1. And it has to be true for each branch as we go. In fact, for this one, I'll just call this the first child, the second child, and then the third child. I'm just going to abbreviate 0.5. It's easier to write. It's still 1/2, right? So how many total branches do I have? 1, 2, 3, 4, 5, 6, 7, 8. There it is. Now the way we, what would be the probability of selecting any one of those? 1 out of 8. And if you multiply 1/2 times 1/2 times 1/2, you get 1/8. So the probability of boy, boy, boy is 1/8. The probability of boy, boy, girl is 1/8. They're all 1/8. And if you add up 1/8, 8 times, you get 8/8. The total probability of all of those is equal to 1. Isn't that nice? Very nice. These trees can help you sort things out. So what's the probability, they're asking, of 0 boys? That means you got all 3 girls. What's the probability of 3 girls? It's the same question. What's the probability of 3 girls? 1/8. It's this type of simplified fraction. So 1/8. What's the probability of 1 boy?
Just 1.
1 boy. Yeah. What's the probability of the family having 1 boy?
Be 1 out of 16.
The denominator still be 8.
Okay.
It's a sample space.
0.5 over.
Excuse me a second. Hello? Yes, Joseph speaks. Okay. Finally.
But if it's out of 8, so.
Okay, appreciate it. Okay, bye-bye. Okay, sorry about that. So, does the relative frequency that,
0.5
no,
over 8.
how many?
0.5 over 8.
25.
No, 0.5 over 8.
No, you can't have half of a family.
Well, because it's out of 3 children.
Well, how many of those have one boy?
Oh.
1,
Oh.
2,
Okay.
3.
I thought you were talking like just one boy.
No, I just said, how many of these can have one
Okay,
boy?
I thought you meant like just one boy. That's why I
No,
went to the 1
okay,
out
I
of
see.
16.
What's the probability of one boy? It would be
It'd be 1 out of 8.
this branch, or this branch, or this branch. And each one of these is 1 over 8. So when you add them together, you get 3 over 8.
Sure.
So 3 over 8.
Okay.
Okay.
That's thinking.
So what happens, this breaks down into you could break it down into a probability distribution. You could say the number of boys and the probability of the number of boys. The 0, 1, 2, 3. So the 1 over 8, 3 over 8, 3 over 8, 1 over 8. They all add up once again, total probability is 1. But you see, you compress all of this into just worrying about the number of boys.
Yeah.
You could do, it's symmetrical for girls. It's the same outcome. Because if you have 0 boys, you have 3 girls. If you have 1 boy, you have 2 girls. 2 boys, 1 girl, 3 boys, no girls. So it's symmetrical in that way. But that's called the probability distribution. You have it's very similar to the frequency diagrams we have. Only now it's a probability distribution.
So frequency.
What's that?
So type of frequency.
Yeah, it's frequencies, right? In a way, right? Okay, so guess what the next one is? List the sample space for 4 kids. If there's 8 families with 3 kids, how many families with 4 kids? How many with 1? How many with 2? How many with 1 kid? How many families can have? How many different kind of families can you have with 1 child?
1.
2, 1 boy or 1 girl.
Oh.
How many different families can you have with 2 kids? 4, because there's 2 choices for each kid. 8 for 3, so how many for 4? 16. 2 to the 4th. See, that's going to be a counting principle we're going to learn later. You got 4 possibilities. You got 2 times 2 times 2 times 2. That's the multiplicative rule. We'll see it later. So this one's pretty easy. What you do is you just take the first one, boy, 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 and you do boy, 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 comma, boy, 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 girl, comma. So I just took the first one, and I added a boy and then a girl. Then I take the second one, boy, boy, girl. I go boy, boy, girl, boy, comma, boy, boy, girl, girl, comma. And then I go boy, girl, boy, boy, girl, boy, 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 girl, boy, girl. Then I do boy, girl, girl. So boy, girl, girl, boy, comma, boy, girl, girl, girl. Then it's girl, boy, boy. So girl, boy, 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 girl, boy, boy, girl. And then it's girl, girl, boy, girl. Girl, boy, girl, boy, girl, boy, girl, girl. And then GGB, GGBB, GGBG. And then the last one's GGB, GGGG. And that's it.
Oh, yeah.
There's 16 of them. So what's the probability of having 2 girls and 2 boys in any order.
1 and 16. 2.
How many have 2 boys and 2 girls?
Oh, okay.
1,
1, 2.
2, 3, 4, 5, 6. 6 out of 16. 3 says a decimal, so it's 6 out of 16. 3 out of 8. It's 0.375. So I could just extend the tree and add another from each of the last 8 nodes. I would add another branch. I have 16 total branches. Each one would be 1 out of 16. So you can just count them up. The number of successes is 6. The total number in the sample space is 16. So it's 6 over 16. And if you can't do it in your head, then you just use a calculator to get 6 over 16. There's your decimal. Okay? All right. So hang in there.
Good, all good.
Do I want to do this? No, this roulette. A modified roulette table has 32 slots. One slot's a 0, another's a 0, 0, double 0, and the others are numbered 1 through 30, respectively. And then they're odd, even, then there's red, blue, or red, black. You're playing a bet that the outcome is an odd number. In roulette, 0 and double 0 are neither odd or even. Technically, 0 is an even number, but not for roulette. So if you're betting on an odd number, how many?
So you can figure out how many odds are in.
How many odds are there in 1 through 30?
Correct.
How many odd numbers are there? Half of them.
Yeah, okay. Yeah, I was like,
Half are even, half are odd, right?
Okay.
What's half of 30? 15. And how many are in the sample space?
32.
32. Now notice I was going to do a decimal, but they don't say. They type it integer or a simplified fraction. So what they want is 15 over 32. So 15 tab 32. It's 15 chances for success out of 32 possibilities. Now, what are the actual odds against winning? Well, how many outcomes don't favor? How many are not odd? What's 15 from 32? 17. That leaves 15 in your favor. So the odds against, you put the number against divided by the number 4. So 17 to 15. All right. Now, when you bet that the outcome is an odd number, in the casino, they pay you 1 to 1. So if you bet $14, how much would you win? Well, you'd win $14, 1 to 1. They didn't say how much. They didn't say how much you would walk away with. They said what your payoff. The payoff's 1 to 1. Now, what if you use the odds? The 17 to 15. What would the payoff be? Well, instead of 1 to 1, you just do 17 to 15. So it'd be 40, not 40. 14 times 17 divided by 15. Instead of 1 divided by 1. Because 1 divided by 1 is 14. So you could expect $15.87 if they went with the true odds. But you see, that's how they make their money. They're always skimming a little bit. They're not giving you, that's why they add the 2 extra numbers.
So that way they could give it sense.
Yeah, because 0 and double 0, like 0 and double 0 are green. They're not red or black, and so if you bet red or black, it's like betting odd or even. You always have 2 more against you. Yeah. Right? So if a red or green one comes up, everybody that betted odd, even, black, red is a loser. Yeah. And so that's right. And if you do win, you don't win the extra $1.87 that the odds dictate that you should for a fair game. That's called a fair game when you pay off according to the true odds. Okay? Follow it?
Yes.
Okay. A couple of review questions here. The blank for a procedure consists of all of the simple events or all the outcomes that cannot be broken down any further. It was written.
Probability. Or
The blank for a procedure consists of all the possible simple events.
sample space.
Examples. Number 2. The classical approach to probability requires that the outcomes are equally likely. Yeah. Not equal, equally likely. The procedure is repeated again and again. The relative frequency for an event tends to approach the actual probability. I didn't tell you this yet, so this is brand new. Let's see if you can guess it.
Well, the procedure is repeated again. Impossible.
No. It's
Rare.
Law of large numbers.
Ah.
You see, if I roll a die 10 times, there's no way I can get an equal number of all 6 of the outcomes.
Mm-hmm.
Even if I did it 20 times or 100 times, I can expect it to be close to 16 for each one, because that'll be 96, plus or minus. But the more rolls I have, eventually the closer I'll get to the theoretical percentage. Now, I think I might be able to show you that. Let me see if I can do that. I'm not sure, so let me see if I can do that.
See if all these years of math are worth it. What's the difference between a dynamic seed and a fixed seed?
What's that?
The dynamic seed and a fixed seed?
I'm not sure.
No. One rule.
Okay, so there I did 1,000 runs. I hit it twice actually. There's 2,000. 1/6 of 2,000 is 333, right?
Mm-hmm.
We would expect 333 of each. You can see that we're between 300 and 350 on all of them. So the more I do this, the closer they're going to get. The law of large numbers says I'm going to get closer and closer because the differences are going to get smaller and smaller the more n I have.
Mm-hmm.
Follow?
Yeah.
That's the law of large numbers. Let me do another 1,000 runs. So there's 3,000. Let's see. Let's do 6,000 runs. There it is. At 6,000, I expect 1,000 of each. So you can see there's 1,000. So you see they're all pretty close. But the difference now is maybe 10 or 15, which is insignificant compared to 1,000. The percentages and probabilities get closer and closer to 1/6. That's the law of large numbers. You see, our empirical is converging to our empirical or to our classical, our equally likely.
What would you use that for?
This is Monte Carlo techniques just to teach.
Okay. So no actual practical use for that.
Yeah. Okay, so I remembered how to do it. So there you go. Law of large numbers.
All those years were worth it.
It's also called regression to the mean. You know, when you have an outstanding, like an athlete like Wayne Gretzky. You guys know who Wayne Gretzky is?
The
Hockey player who just went. He came on the scene and he broke all the basketball player. You know Michael Jordan? You know Michael Jordan? Phenomenal, right? He broke all kind of records.
Right.
Everybody expected him to, they call it regression to the mean. They expected him to get back to what was average.
Okay.
Because the law of large numbers says that's what's supposed to happen. But that's why he's a phenom. That's why he's above the average. That's why he's a star. Because he didn't regress to the mean. He didn't come back to what expectations were for a typical player. He's not typical.
Okay. The more times he throws. Yeah. Chances that he throws strikes and balls would equal out.
Everything, law of large numbers takes care of everything eventually. It's like when I told you, if I flip a coin and I get 10 heads in a row, eventually they're going to even out because I'll get 10 tails in a row sometime. But over the long haul, it's going to be 50-50, unless somebody screwed with the coin. Which of the following is not a principle of probability? Probability of any events between 0 and 1. The probability of an event that's certain to occur is 1. The probability of an impossible event is 0. So all events are equally likely. No, they're not. We can assume they are, we can theorize they are, but
it says in any probability.
any probability, right?
Yeah.
It doesn't always true. So what's the probability of an event divided by the probability of its complement?
What?
It's up there.
Odds against
No.
4.
No. See, it's 4A is in the numerator. Against A is in the denominator.
Okay. Gotcha.
So the numerator always carries. See, 4A is in the numerator. Against A, it's in the numerator. Always, whatever's in the numerator is what's for against.
Okay.
So, since it's in the numerator, it's for or in favor of. So the actual odds in favor of. Okay? Okay, so that's it for this section. We can move on to the next section. Might be a little bit longer today, I don't know for sure. We'll see. Addition rule and multiplication rule. We've touched on those a little bit, but we'll see how we can. So this is a repeat of what we just we kind of talked about. What does PA represent?
I represent the probability 4.
Now A is the event of someone having blue eyes, selecting somebody with blue eyes. So what's P of A represent?
That would be the probability.
Selecting an adult with blue eyes. So P of A bar would be the probability of
Not select.
selecting an adult who does not have blue eyes. Right? See, they want you to make sure that when you see the P, it's probability. When you just see the A, that's the event.
Okay.
So that's the event, that's the probability of that event.
Okay.
Now they're going to throw in a new one. Vertical line. It's what we call a conditional, which means it's a given. So the way we read that, PMV is the probability of selecting a male given the person has blue eyes. This vertical line means given. That already occurred. So what we do is we're shrinking the sample space because the total sample space includes people that don't have blue eyes, green eyes, whatever, brown eyes. But we're just saying we're only going to use people that have blue eyes. So the sample space is shrunk. It'd be kind of like this. Here's my sample space. And it's half men and half women. And then here's the blue eyes. So we're going to select this region because we're already going to select this circle. So it's the probability of getting a male given that someone has blue eyes. That's what it means given. You can just put that right in there. Now, is it the same? Are they the same? The probability of B given M. Well, if you looked at this, if I give these codes, if I say this is 1, 2, 3, and 4 as just regions, then the probability of M given B on top here would be 2 out of 2 plus 3. Right?
Correct.
Probability of a male given blue. given blue is 2 plus 3, Mayo would be 2. So I'm just taking this part over the sum of those two parts. The probability of B given M, now this is what's given. See, this is what I'm shrinking the sample space. Now this would be 2 over 1 plus 2. Now I'm selecting the blue given that it's a male. So it's total different regions. And there's different counts in each region, if depending on the sample that we pick. So no, they're not the same. Because the DM represents the probability of getting someone with blue eyes given that a male has been selected. I picked the wrong one. It says yes, that's why. It should be the one that says no. It was a distractor and it distracted me.
So,
unfortunately. Okay, number 3 is the 5% rule. This is the 5% rule in terms of sampling. We're going to introduce another idea of independent and dependent. When you do sampling, you can do it with sampling methods. You can sample with replacement, or without replacement. Typical problems they'll throw at us is like, I got a bag with 5 red marbles and 4 blue marbles, and what's the probability of selecting a red one? It'll be 5 out of 9. What's the probability of selecting 2 red ones if I don't replace it? So I would draw my tree diagram. So I got 5 red and 4 blue in my bag. So on the first, see that tree diagram helps. So the first red would be 5 out of 9. So the first blue would be 4 out of 9. The second red, now it would all depend on whether I replaced it or not. If I did replace it, I'm back in the same sample space. It's 5 out of 9, and I would just have 25 out of 81 I would just multiply. That's the multiplication rule. And that's the only one I really care about because they want 2 red. But if I didn't replace it, then one of them would be gone for both the red and the sample space. I only have 4 red left and I only have 8 marbles. So now it'll be 20 out of 72 for the 2 red ones. So that's the difference between them. And we call with replacement independent because I have the same sample space. So the two picks are essentially independent. If I keep the same sample space, it doesn't matter. One pick doesn't affect the other. But if I don't replace it, then I change the sample space, so now it's dependent. So if there's 16 million adults, that's essentially 16 million, and I'm going to randomly select 1,235 adults without replacement. Are the selections independent or dependent? Well, without replacement is dependent. So B, the selections are dependent because the selection's done without replacement. That's technically true. However, 1,235 compared to 16 million is like minuscule. It's like 0%, essentially. Let's see what it is. Let's look at it. If I do the division, I would get 1,235 divided by 15,958,866. You see, that's E5, E minus 5 means put 4 zeros in front of the 7. So it's 0,0007. And that's essentially, if you do it this way, it's like choosing 1 out of 13,000. That's like minuscule. So what we do is we say, if the size of the sample is less than 5% of the population that you're choosing from, then we assume independence. So can they be treated as independent? Yes, because the sample is less than 5% of the population. Right? It's like 0.0000. It's like 0.007% of the population. It's really, really small. Got it? Okay, so without replacements dependent, with replacements independent. We'll keep that in mind, it'll come up again. And the 5% rule, it's real nice to use because that'll come up again too. We'll show you why that's going to be in our favor going forward. Okay, number 5. A research center poll showed that 77% of the people believe that it's morally wrong not to report all income tax returns. What's the probability someone does not have this belief? 0.23. Yeah. Right? If 77% do, then 23% don't. Okay? By the way, just in passing, that's the one thing where they catch you on audits, is if you don't report income. Everything else you can finagle, or get your tax expert to help you with, but don't skimp on your income. Don't lie about income. They'll get you every time. Anyway, whatever that
Because they compare to companies W2 or W2.
they'll always get you. It's just the way they are.
Just don't report at all.
A man observed a sobriety checkpoint conducted by the police department. He saw 660 drivers were screened, 6 were arrested. So that's where they got the probability. 6 divided by 60, 660 is 0.0090. That's where they got that probability of W. So W is somebody that's screened and arrested for drunk driving. So what does PW bar represent? Or denote? What does it represent? Probability of not being arrested.
Correct.
And so, which one is it? C. Probability of screening a driver and finding out he or she is not intoxicated. So what is that probability?
You subtract that 0.0090.
Right. So here's how easy way to do this. Here's how I do it. Whatever number you're going to pick, it has to add up to 9. So it'd be 99009, and then the last one always adds up to 10. So it's 99091.
Okay.
So 99091. Oh, I did it on the wrong one. 99091. So just so you see that, so let's say we had the probability was 3418. If that's the probability of A, then the probability of A bar would be 6582. These add up to 99910. See that? That's the easy way to do it. Or you can use a calculator and punch them in and go through the process.
Would you just subtract it from the 1,000? Or I guess the 1?
Yeah, you say 1 minus
it.
1 minus 0.3418. It's that formula right there.
Oh, okay.
All right? 6582. I just do it in my head. It's real easy.
Yeah.
Okay. You don't have to, but you can use the calculator. It's okay. All right, number 8. Number 9. Okay, here we go. We're going to have a bunch of these in a row. So here's what I'm going to do. I'm going to take the first one, and this is a 2x4 contingency table. You got 4 restaurants and two categories. So there's eight boxes. But I don't have marginals. See, they want to know probability of getting foods not from restaurant A. So I have to add up all of them, and then I have to add up these and subtract it from the total. Okay, but here's an easy way to do this, because we're going to have more of these. So what I'm going to do is I'm going to open this up in Excel instead of StatCrunch. So you see it gave me It gave me everything I need, except I need marginals. Let me see if I can make this smaller. This one. There we go. And then, so what I'm going to do is, you know how to do this? What you do is I want marginals. So what you do is you do equals sum. It's B2, B3. So you do B2 colon B3. And then you just go Control C, Control V, copy. Now I want to do the horizontals, so I do sum, parentheses, it'll be B2 colon E2. So it's going to go all the way B2, C2, D2, and E2. Oh, I forgot to put equals there. Equals. There we go. All right, so that's the sum of the first row. Now to copy that, I just do Control C and Control V. Okay, so my grand, these are all the marginals. So my grand total is 1095, and so that's going to be my numerator, or I'm sorry, my denominator. And then they want to know how many are not restaurant A. So I take the total in the numerator, 1095, and I subtract restaurant A. That leaves all the other restaurants. And I divide by 1095. Isn't that easy? Rather than summing up the other three. All right, so 677. That's the probability. That's essentially the probability of being in any one of these six.
What's that number? So we're 676712328.
I don't know. So that's how you do that. Okay, so now when you're doing this for yourself for homework, here's what you got to do now. Watch. Oops. Okay. The next question. It's the same setup, but the numbers changed. So rather than copy it and go through that whole process again, what I do, I go over here and I just change these numbers. I do 335, and then everything will be taken care of. All the marginals will be automatically updated. All I got to do is put in those 8 numbers. It's a little bit time consuming, but a lot less than if you have to start over every time. The last one's 10. So see everything updated and all the marginals. I put in the raw data. Probability of getting an order that's not accurate. So that's the bottom row. 135 over 1118. See that? So I do 135 divided by 1118. I wish they would use the same box over and over, but they don't. So 0.121. Next question. I got oops, I keep hitting the wrong button. Sorry. I got to update the numbers again. 316. 30, 276, 53, 239. Of course, there's always a data entry is always a source of non-random error. That one stays the same. Okay, so probability of getting an order from restaurant A or an order that is accurate. So now we're going to have to do with the addition rule. This is a union. Or is a union. Because essentially what's happening here, restaurant A is these two, and not accurate is these 4. But you notice that this one happens twice. Because I got it in this column and this row. So I have to subtract it once. So these aren't the restaurants, these are just generic A and B. This is equal to the probability of A plus the probability of B minus the probability of the intersection, because this is in both of them. See that? That's the addition rule. Now the thing of it is that the denominators are all the same. It's the number in the sample space. So this is the number in A plus the number in B minus the number in the intersection. The intersection, it's easy to see on here. It's the intersection of this column and this row. It's 30. So you could do it that way. Probably the easiest way is to take the number in A is 346. The number in B, which is the bottom row, is 131. The number in the intersection, I put a minus there, that should be a plus. The minus comes now. Minus the 30, because the 30 occurs in both the 346 and the 131, so I can't count it twice. And then I divide by the total. The total is 1082. So it's 413.413.
Okay.
This is called the addition. Called the addition rule. I did something wrong.
Are you sure you minus 30?
Well, of course. Make sure I got all the numbers right. Yeah, I got all the numbers. I got all the numbers right. Oh, it's an order that's accurate. I did inaccurate. See, I did the bottom row instead of the top row. So that was my mistake. I just read it wrong. So if I just curse back up here, I could change. The 346 stays the same. Now we have to add 951. And then we subtract 316. There you go. So it's 907. I just read it wrong. My bad. But luckily we have a second chance. Okay? Are the events of selecting an order from restaurant A and selecting an accurate order, disjoint? In other words, is their intersection empty? That's kind of an obvious question, isn't it? Is their intersection empty? No. They got 316 that are both in both categories. So it's not a disjoint. They're not disjoint. So the events are not disjoint because it is possible to receive an accurate order from restaurant A. It's possible for both of them to occur. You see what disjoint means?
Right.
If that intersection was empty, if there was 0 in there, yeah, then they'd be disjoint. Okay? All right. So next question, I got to update again. This is the quickest way I know how to do this. Believe me, after all the times I've taught this class, this is the quickest way. I know it's a little bit time-consuming, but not too bad. Used to have to do this by hand, and I wondered, is there a quicker way? And then I worked it out on my computer. Everything updates, which the margin is what we really need. You know. So here, what's the probability of getting an order from restaurant C or an order that's not accurate? So now we're doing C in the bottom row. So it's this column and this row. I think I got it right this time. So I would take the number from C, which is 282. I would add the bottom row, which is 148, and then I would subtract where they intersect, which is 40. 40 is the repeated. And I would divide by the total, 1158. So 337. Let's see if we got it this time. Yay. And they're going to ask you the same question. Are they disjoint?
No.
No, they're not disjoint, because it is possible to get an inaccurate order from restaurant C. It's possible for both of them to occur simultaneously. We good? All right. Next question. Once more, I keep hitting the wrong position there. So 333, 280, 39, 142, 38, 58, 39, 16 is okay. Assume that the selections are made with replacement. So that means we keep the same sample space. We've got two orders. So we're going to need a tree for this. So if two orders are selected, find the probability they're both from restaurant D. So D, not D. So from D, it would be 140, I'm sorry, it would be 158 out of 1145. That's the first order from D. All I really care about is this branch. The second order from D is the same number because it's with replacement. So it's 158 out of 1145. The tree helps. I don't need all the other branches because all I care about is two orders from D.
Can you add those together?
No, you multiply. Multiply. So the probability of two orders from D would be, why do I keep doing that? So the way to do this is put it in parentheses, 158 divided by 1145 squared. So the probability is 0.019. The events are independent because choosing the first order does not affect the probability of the choice in the second order.
Correct.
Now they're going to ask us to make it without replacement. So what changes?
Take out the first sample size.
There's one less order from D and from the total. So that's why we like to use independence, because now I got to write two fractions. That's the problem. I got to write 158 divided by 1145 times 157 divided by 1144. It's not going to be that big a difference. It's 0.189.
Correct.
I'm sorry, it's 0.0. They want 4 decimal places. I was lucky there was a 0 after the 9, and they didn't hold it against me. See, there's a 0 after the 9. They wanted 4 decimal places there. But since it was 0, it was okay. Now they want 4 decimal places here, so it's 0.189. So there is a difference, isn't there? Yeah, big difference. The events are not independent because choosing the first order affects the probability of the second order. This is where you can see now if you have this is why when you have a large population to choose from, you don't want to have to change fractions. You just want to keep a constant probability because it's easier just to use an exponent. Because if the probability is real small, who cares? You see the difference here, you have to go out to the 4th decimal place to figure it out. But most people would say, well, it's rounded out to 2%, 0.02. But not for this question. Okay. That was 14. Yeah, we do 15. We do a lot of these because what it's doing is giving us a chance to see a lot of the probability rules and how we put them together. These are all relative frequencies, obviously. because they're observed, they're empirical. Assume the selections are made with replacement, so it's going to be the same thing, only now it's like, if two orders are selected, find the probability they're both accurate. So now it's the top row. 979 out of 1118 squared. You see, all I'm doing now is accurate 1, not accurate. Accurate 2. So it'll be,
Yeah, okay, so we 979 out of 11.
11 what?
18.
So we'll just square that.
11, 18.
1118?
Yeah.
Excuse me, okay. So 979 divided by 1118 squared. 767, 4 decimal places. 7668. They're independent. Now, if we do it with replacement, without replacement, excuse me, it's 979 divided by 1118 times 978 divided by 1117. 7667. You see why they're going 4 decimal places, and these events are not independent. Because this was 978 over 1117. Okay? I think we hammered that one home. We got the difference down between independent and dependent. That was 15. I think there's still a couple more of these. All right. So 330. I don't see why they couldn't use the same numbers.
I was going to say, because they ask different questions each time.
But still, use different.
That's what I'm saying. You could have used the same numbers.
I know. That's what I thought.
Time.
So if one order is selected, find the probability of getting an order from restaurant A or restaurant B or an order that's not accurate. So now you have 2 orders. It's A or B or an order that's not accurate.
Okay, so they're all independent.
No, they're not independent. A or B are independent,
From restaurant A
but not,
or in order.
but not accuracy, because this occurs twice. So you can take these 2 for A and B, but then when you add the whole bottom row, you have to subtract those 2 twice. You have to subtract both of them.
But when that's
Because what we're doing is we're including 1, 2, 3, 4, 5, 6. You could almost just subtract those 2 and that'd be the same thing.
yeah, wouldn't you?
Right? Because we're including 6 of them. Because it's either this or this or this.
Right.
So we're adding these 6 boxes.
Right.
Which means let's just subtract those 2 from that and divide by that. Let's see if it works.
I'll go ahead and say
So it'll be 1126 minus those 2, 233 and 149. Because then we're counting every other one, so we're dividing by 1126, and it should be 661. 661. So it's just using 2 numbers instead of 6 numbers.
Yeah.
Or 4 numbers or whatever. All right, good enough?
Good
I think
enough.
there's one more. This is the last one. Pretty sure. Okay, so 311, 263, 238, 132, 37. So you'll have several of these in succession. So you'll want to set it up like this. You guys know how to use Excel.
Right.
And if you just open it up in Excel, it's got all the headers and everything. You just have to figure out how to do the marginals, which aren't that difficult.
watch that video.
If 3 different orders are selected, find the probability they're all from restaurant D.
So it's gonna be 148 over 1086. No, it's just gonna be,
Yep, cubed,
right,
because it's 3 branches now.
yeah.
And it doesn't say anything about
Different orders.
independent or dependent.
Maybe that's the next one.
It doesn't say anything in there one way or the other.
No.
So let's try it
Yeah, they're all
using independent. Well, first of all,
uses in chat.
well, technically 148 is restaurant D. It's not, it's more than 5% of 1086.
Right.
So let's be honest about it. So the first one will be 148 over 1086. And then the second one would be 147 over 1087. And the last one would be 145. Oh, yeah, I went the wrong way. Thank you. 146 out of,
And you forgot a zero on that.
okay, 1084. There we go. 0025. All right, so before we leave that, let's do this. Let's see how close it would have been if we had just assumed independence. This way, we know we got the right answer, so I'm going to do cubed, right? Math 3 cubed. 00, we would have said 0025. It would have been okay.
Good.
But if you do it one way and it says wrong, then do it the other way. All right. Is this the last one? Yeah, we're done with them. Okay. Yeah. This is number 21. All right. Use the following results for a test for marijuana use, which was provided by a certain drug testing company. There's 147 subjects with positive test results. There's 26 false positive results. Among 152 negative results, there's 3 false negatives. Hint, construct a table. All right, so let's take the hint. Close that. And open up StatCrunch. We'll construct a table. All right, so we got positive.
Just add them all up.
No, you gotta be careful here. There's 147 subjects with positive test results. So we'll say positive. That means there's negative. Then we're going to say, see, that's the marginal, 147. And let's say true, false. So 26 false positives. That means there was 121 true positives. Of the negative results, there's 152 negatives. 3 were false negative. That means 148 were true negative. So how many subjects were included in the study? So that's easy enough. 199 or 299. Right? How many subjects did not use marijuana? Now, gotta be real careful here.
148.
The true negatives didn't use marijuana. The false positives did. Or
Did not.
did not. So 26 plus 148. This is one where you might have to do this. You might have to say, use, not use. Positive, negative. So the positives are still 147, and the negatives are still 152. That doesn't change. But if you're a true positive, that means you used. So that's 121. That means this stays at 26. But however, if you're a true negative, that means you didn't use. So that's 148. And this is 3. You see, now, how many total subjects did not use? So that marginal is 174. This one's 124. This is 2.291. So you have to be careful here, because the false and true are with the test, not with the use. So we have to change. Although we knew when we said it that we were going to add up 26 and 148. You don't need this. You can just add up those two. So and you would divide 174 by 299. So your relative frequency is 582. Oh, they want the raw number, 174. Oh, they're saying we're wrong.
147 or 148.
Did I do something wrong here?
In your math, unless you added up 147.
Oh, it's 149. That's what it is, 149. Yeah, you're right. I see that. So this is 175. I don't know. I just did bad arithmetic.
No, where did the 149 come from?
3 plus 149 is 152. I said 148.
Okay. So
I did bad math.
Okay.
You should have said something.
I didn't. Good job.
But we found it. It's okay. So what's the probability selected subject did not use marijuana? That's the 175. So I'll just do second enter and do 175 instead of 174. 585. That's the probability that they didn't. It's so randomly selected. That's 59%, 58.5%. Okay, but you see what we had to do here as far as the table. It says construct a table. So I constructed a 2 by 2, and I still got marginals. We don't need all the marginals, but it helps because when you add these two and these two, you should get 299 both directions. Okay, so that was 21. Let's see, the next one's 25, I think. A principle of redundancy is used when system reliability is improved through redundant or backup components. Assume that a student's alarm clock has a 12.5% daily failure rate. What's the probability a student's alarm clock will not work on a morning of an important exam?
You have to find out.
0.17, 0.127. So guess what they're going to do? They're going to say 2 alarm clocks. They're both the same model.
We would add both.
Don't add.
Multiply.
Work, not work. Work, not work. See, this is, all I need is this one. So it's 0.127. And they're independent because they're different clocks. They just happen to have the same manufacturer, so they have the same probability of. So, what's the probability that they both fail? The only way they both fail is on the bottom branch, because on this branch this one works, on this branch this one works, and on this branch they both work. So, on the 3 branches, you got at least one of them working. But the only one where it doesn't work is the bottom branch, so that's 0.127 times itself. So it's 0.016. They went 5 decimal places. 0.01613. Guess what the next question is going to be? 3 of them. So all you got to do is 0.127 cubic. So math 3. So 0.00205. 0.00205. So that's 1 chance in 500. So you should make it through the year, okay?
Should.
You see where I got the 1 chance in 500? All you got to do is change it. See, 1 chance in 488, so essentially 500. Do the second and third alarm clocks result in greater improved reliability? Sure. Because you're always certain that at least one alarm clock will work.
Yes, because it's so.
Or yes, because total malfunction would not be impossible, but highly, highly unlikely. That's a better answer. You can't assume that you won't end up with 3 of them all failing. There's 1 chance in 488 that that'll happen. But you see why you use redundancy in electronic systems like for spacecraft and airplanes. Because you have to have at least one of the systems working correctly, or circuits. That's the idea of redundancy. That's the same redundancy again. Okay, so you got that one down, right? So among 6,401 cases of heart pacemaker malfunctions, 335 were found to be caused by firmware, which is software programmed into the device. If the firmware is tested in 3 different pacemakers randomly selected from this batch of 641, and the entire batch is accepted if there's no failures, what's the probability the firmware in the entire batch will be accepted? So what's the probability that the first one will be, well, first of all, let's do this. 335 divided by 6, this is the first one. That's 5, it's greater than 5%, so I can't use the 5% rule. So the probability that the first one is defective, there's 335 bad ones out of 6,401. Okay? Let's see, wait a minute. Oh, you want the entire batch selected, so. Okay. So if there's at least one bad one. So, good, bad, good, good. We need 3 good ones, right? So what's the probability of the first one being good? It'd be 6,066. $6,401 minus 335. 6,066. So the probability of getting a good one is 6 over 6,635. Right? That's the probability of a success. 6,401. What am I doing? 6,401. All right, so once I selected that one, there's one less. Now I select another one, it'd be 665 over 6400. The next one would be 6064 out of 6399. That's the probability of getting 3 good ones in a row. And I can't use that first fraction and just cube it because I can't use the 5% rule. although we'll check to see if it works. So the first one will be 6066 divided by 6401. The second one will be 6065 divided by 6400. And the third one will be 6064 divided by 6399. So it's an 85% chance that that it'll pass muster. The procedure is likely to result in the entire batch being accepted. Now, let's just see for the sake of argument if I would have done 6066 divided by 6401 cubed. Yeah, 851, I would have got the same answer. Now, I could have done this another way also. I could have used a complement. I could have subtracted the 335 divided by, no, that wouldn't have worked. Because that's for all three. No, sorry, I can't do it that way. I was thinking of something else. So that's what we got to do. We have to take the complement of 335 from this, which is the 600. 6066. That's the number of good ones. And I just do the probability of 3 good ones in a row. Because that's the only one that matters. Because if I get at least 1 bad one, boom, we're done. Right?
Yeah.
Okay. All right. But you could do this either way. Once again, if you want to do it the easy way on the bottom there, and you get a wrong, he says no, then you do it the other way, the long way.
Or I guess the right way.
The right way. The easy way. I don't know if it's the right way, it's the easy way. Easy way. Before 230. Okay, now this one, we're going to use it the easy way. In a study of helicopter usage in patient survival among 43,464 patients transported by helicopter, 254 of them left treatment center against medical advice, and the other 43,210 did not. If 50 subjects are transported by helicopter or are randomly selected without replacement, what's the probability none of them left the treatment center against medical advice? So I'm going to use the 43210 divided by that to the 50th power. Okay, you see why I'm going to do that? Because 254 is less than 5% of that. All right, so we're going to do 43, 210 divided by the 43, 464. I'm going to raise it to the 50th power. That's not bad. 746. What we have is we have one branch. They're all the same.
Yeah.
And we can assume independence because of this 5% rule of the size of the sample. Okay? And I said 254 divided by that, but the sample's only 50. 50 divided. Oh, that was true on the last one too. The sample was only size 3. So I was wrong on that one. So I'm missing a finer point there. It's the sample size. It's not the number that are defective. Okay, that's the end of that section. How about that? We're now going to move to section 3. There's not a lot of questions in this section. There's only a couple, but we'll go through them pretty quickly. This is at least one. The notion, you guys know the idea of at least one. Given any sample size, you would say that the probability of at least one is equal to 1 minus the probability of none. Because the complement of at least 1 is none. Right? Like in a probability distribution, x can take on values from 1 to n. And the probability of at least 1, the complement is 0. So it's easier just to find this probability and subtract it from 1. And that gives you your answer. Because every other value of x contains at least one outcome. Or one success. Right?
Yeah.
So that's the complementary rule. Probability of at least 1. And sometimes people write it. The probability that x is greater than or equal to 1 equals 1 minus the probability x equals 0. That's another way to look at it. Because when you have a distribution, it usually runs from 0 to n. Those are the possible outcomes. It's numerical. It's usually a numerical distribution. So find the probability when a couple has 2 children, at least one of them is a girl. 3 out of 4. There's 4 possibilities.
2 children.
There's only chance you can't have one girl is if you have 2 boys. So it's 3 out of 4. See, you would subtract 1/4 from 1. You remember? We had it for 3 and 4 children. For 2 children, there's only 4 possibilities.
Right.
Sample space is
Okay.
boy, 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 girl, girl, boy, girl, girl. So having at least one girl is 3 chances out of 4. So we have to write it as a decimal, I think. Yeah, 3 out of 4. That was 5. Number 6. Assuming boys and girls are equally likely, find the probability of a couple having a baby boy when their 4th child is born, given that the first 3 children were all boys.
So,
What's the probability of a couple having a baby boy when the 4th child is born, given that the first 3 were boys? So what's the probability of a boy?
8. It'd be 1 out of 8.
No, you're missing the point. Read what it says. It says find the probability of the couple having a baby boy.
1 out of 2.
1 out of 2, it doesn't matter what happened. They're all independent. It doesn't matter. There's no change in the sample space. It's always 1 out of 2. So it's 50%. See, they're trying to trick you into thinking, well, they had 3 boys, so it's going to change something. It doesn't matter. Yeah. Any child being born, it's 50-50. That's what they said at the very beginning. It's equally likely. So be careful with that. Don't read too much into it. Here's another at least 1. In a certain country, the true probability of a baby girl is 0.483. Among the next 4 randomly selected births in the country, what's the probability of at least one of them being a boy? So, draw your tree diagram so you can see what's going on. Boy, girl, 0.483, right? So this is 0.517. 483? Yeah.
Right.
What's the probability of at least one boy? Well, what's the probability of no boys? It'd be 0.483 to the 4th power. So every other branch is going to have at least one boy. So I take this times this times this, I subtract it from 1. I find the probability of none, and I subtract it from 100%. So it'll be 1 minus 0.483, yeah, to the 4th power. See, that's my probability of none. I subtract from 100%. And that gives me the probability of at least 1. 946. Okay? See how the tree diagram always helps me out? I know what it is I'm doing then. I don't need the whole tree, I just need to put it in a form that I understand why and then whenever you have a tree, it's always multiplication. You always multiply, it's the multiplication rule, always. 7, couple more here, 14, let's see what 14 says. Okay, silly question, but it works. In the experiment, college students were given either 4 quarters or a $1 bill, and they could either keep the money or spend it on gum. The results are summarized in the table below. So the top row is 4 quarters, the bottom row is a $1 bill. This column is purchased gum, this column is kept the money. Find the probability of randomly selecting a student who spent the money, given that the student was given 4 quarters. So the only thing that matters is the top row, because it's given that they have 4 quarters. So what's the probability that they spent the money? It'd be 30 out of 47, because the margin was 47. So 30 out of 47. Six, 3, 8. And the next question is kind of silly. It says, find the probability of randomly selecting a student who kept the money, given that the student was given 4 quarters. So that's just the 17 out of 47, because it's still this top row. So you could just, 2 ways to do it. You could either divide 17 by 47, or just take the complement of this. 3, 6, 2. See it? 3, 6, 2. Oh, I wrote it wrong. I put 6, 3 instead of 3, 6. This is why they give you more chances than one. I keep doing it. What do the preceding results suggest? Be careful. All we know is that we don't know anything about the other lower half. All we know is the top row. So a student given 4 quarters is more likely to spend the money. That's the higher percentage. That's all we can say about the results that we use. We can't say anything about people who had a $1 bill unless we do more calculations, but we didn't do the calculations. They're basing it on the calculations we did.
Okay.
Yeah, don't read into it. See, this is 7, that's 14. That's the same kind of problem. All right. The data represent results of the test for a certain disease. Assume one individual from the groups randomly selected. Find the probability of getting someone who tested positive, given that he or she did not have the disease. So the only one that counts is this column, because they didn't get the disease. So positive is 15 out of the total. That's the marginal would be 141. 15 out of 141. See, given that he or she did not have the disease, so that's all that counts right there, that column. So it's 15 out of 141. 15 divided by the sum of 15 plus 106.106. Okay. I think that's it for that section. We're going to go ahead and finish up here. A little bit of what we call counting. And what we're going to do is deal with what we call permutations and combinations. You know what? Let me see something here. I think I forgot something. Let me double check, see how important it is. No, we did that one before. Okay, so let me go back to 4.4 then. counting, a thief steals an ATM card and must randomly guess the correct 5-digit PIN code from a 7-key keypad. Repetition of digits is allowed. What's the probability of correct guess on the first try? So it's pretty
On
easy.
the first try?
It's pretty easy. Yeah, first try. This is what the multiplication rule.
Correct.
It's like a tree diagram. They all have to be true. What's the probability he gets the first one correct? Or how many chances are there for the first one? 7, 7, 7, 7. Because repetition is allowed. So when you multiply them, that's how many possibilities there are. And to get it on the first try, it's one chance. 1 out of 7 to the 5th. That's the probability. It says type an integer or fraction. So we need the number 7 to the 5th power. 16,807. So the fraction is one chance out of 16,807. Oops. Did I do it right? 7th. Repetition of digits is allowed. See, if you couldn't use same digit again, then you have 6, 5, 4.
Like 7 to the 7, 7 to the 7, 7 to the 7.
No. What I have here is the number of possible 5-digit numbers where there's 1 out of 7 choices for each number. You know, if it were 10, then it would be 10 times 10 times 10 times 10, it'd be 100,000. But since there's only 7, 7 times 7 times 7 times 7, which the number's right, 7 to the 5th power, and there's only one correct code
For the first try.
Yeah.
So.
Let's simplify your answer.
Yeah, well, that's as simple as it can get. Oh, they don't want the fraction. They want the number of possible codes. They don't want the fraction. They want the 16,807. I didn't read the problem correctly. Okay. So what's the probability?
1 in 16.
So that's the probability, one chance out of that many. I just didn't read the problem correctly.
I was doing that the other night.
Okay? Now, the numerator would change according to how many chances he took. If he did it twice, it'd be 2 out of that, right? Okay. 3 times, 3 out of that. Okay. But the thing of it is if he did a pattern, he'd have to take that many chances to get them all. I mean, he might get it before he went through all of them, but you never know. Okay, that was 5. Let's do 9. What happened to? Oh, there they come. Okay. If you know the names of the remaining 4 students on the spelling bee, what's the probability of randomly selecting an order and getting the order that was used in the spelling bee? 4 students. See, there's 4 slots. How many possibilities are there for the first student? 4. Once you choose that one, there's 3 left because you can't repeat. See, now you can't repeat, so it's 24. 24 possibilities. No, they want the probability, because you see, they're asking for the probability, so it's 1 out of 24. Good? You good with that one? See, you draw your slots, and you just figure out how many go in there. This one's yours. Presidential candidate plans to begin her campaign by visiting the capitals in 3 of 49 states. What's the probability she selects the route of 3 specific capitals? How many different ways could she select 3 different capitals? 49, 48, 47. So it's 1 divided by that number, whatever that number is.
Oh, okay.
Wow, 110,000. So it's 1 over that number.
So like, no,
Now, this is actually a permutation. A permutation is a selection where order is involved versus a combination where order is not involved. So permutation, permute, means to change with order. So permutation involves order, involves selection with order. And that's what this one involved, order. This route. Route means order. So, from n objects, selecting R of them. So what we do is we call it pick n pick R. And the formula for this is n factorial over n minus R factorial. You guys know what factorials are? N factorial is n times n minus 1 times n minus 2 times 3 times 2 times 1. So for instance, 5 factorial is 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 factorial. Right? Like this is 5 times 4 factorial. It's just, and 1 factorial is equal to 1. You're not really multiplying anything, but it's equal to 1. And here's the kicker. By definition, 0 factorial is also equal to 1. So, combination, a permutation. A combination involves selecting a group of R objects from a set of n objects. These are on the handout, by the way. And here you call it choose, n choose R. So the word for combination is choose, so that you have a C, and the word for permutation is pick, so you have a P. But it's the same idea, just so n choose R is n factorial over n minus R factorial times R factorial. Because this takes the order away. I think I got those right. Did I get them right? Yeah. Now, we can calculate those, or we can let the calculator do it for us. So this last one, watch this. This is 49 pick 3. So what I do is I do 49 I do math, and I'm gonna go to the, all the way to the right, so I go left. You see it, number 2, NPR, and then I put R. So this tells me N is 49 and R is 3, and I'm picking. I'm doing a permutation. So I get the same number. See that? See, because we have 49 on a route, we're picking 3. There it goes. Okay. And you can do factorials too. Watch. I can do 6 factorial. Watch. Just do math. See number 4. 6 factorial is 720. That's 6 times 5 times 4 times 3 times 2 times 1. So the calculator can do a lot. No matter which formula you use, or you can just let the calculator do it for you. And you can figure out a lot of things for accounting, especially like with lotteries and stuff like that. When testing for current in the cable with 9 color-coded wires, the author used a meter to test 3 wires at a time. How many different tests are required for every possible pairing of 3 wires? So this is combinations. So he's taking 3 out of 9, so it's 9 choose 3. So 9 chooses 3. So there's 84 different ways to do that. He's got to run 84 tests to get them all done. So if I were to do that using the formula, just to show you how it works, then 9 choose 3 would have been 9 factorial over 6 factorial, 3 factorial. These two always add to this. You see, because if R is 3, then N minus R is 6. And see, watch the math. It's 9 times 8 times 7 times 6 factorial over 6 factorial times 3 factorial. That cancels. And this is 3 times 2 times 1. So the 3 cancels here, the 2 cancels here, so you got 7 times 12. 7 times 3 times 4 is 84. That's where it came from. So you can work it out with the formula, or you can rely on the calculator to give you the answer. It's the setup. You have to know, is order important? Use a permutation. Am I just getting a group? It's a combination, where order doesn't matter. So if you have a group that has president, vice president, secretary, treasurer, that's order matters, because you're selecting them by specific. Or if you're putting paintings on a wall, there's positions. You're not just selecting 7 paintings, you're putting 7 paintings in a row. That's permutation there. So you just have to, in the context of the problem, you have to figure out whether order is important or not. In a small private school, 4 students are randomly selected from 19 available students. What's the probability they are the 4 youngest? Well, the numerator is 1 because there's only one group with the 1 youngest. But the denominator is 19 choose 4. So here's I can do this. I can just click second enter and put in a 1 and a 4. So there's 19 choose 4. That's my denominator, 3876. So the fraction is 1 divided by 3876. Realistically, there's only one group that has the 4 youngest. That's just the way it goes. Number 17. Winning the jackpot in a particular lottery requires that you select the correct 4 numbers between 1 and 25, and in a separate drawing, you must also select the correct singles number 1 through 52. So, order doesn't matter. Doesn't matter how you select them. So it's a combination. So it's 25. So I'm just going to do second enter. I'm going to change to 25 or 19 to 25, and then choose 4. So that's the way you can pick the 4 numbers. How many ways are there to pick the last number? 52. So times 52. There's only 52 ways to pick a number from 1 through 52. So the probability is 1 out of that number. So it's a fraction 1 divided by 65789. Getting it?
Yeah.
Next question is 22. A classic counting problem is to determine a number of different ways that the letters incidentally can be arranged. Well, how many letters are there? 12? So there's 12
You
factorial.
might wanna count that again.
There's 12 factorial ways to arrange it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If you got 12 items, then there's 12 factorial ways to arrange it. Right? Because I would have 12 slots. There's 12 ways to pick the first letter, 11 ways to pick the second letter. And when I get all the way down to the last one, be 12 times 11 all the way down. So it's 12 factorial. However, there's repetitions. I can't distinguish between the two i's, so I divide by 2 factorial. There's two of them that are going to be, I can't tell them apart. And there's also 2 l's, which I cannot tell apart, and 2 m's. So it'll be divided by 2 factorial times. All the other ones are 1 factorial, and we don't need that because it's equal to 1. In other words, I would have 1 factorial 6 times. That doesn't, I don't really need them because there's no mathematical sense to that. But I can't tell the difference between 2 n's, 2 l's, and 2 i's. So that's my answer. So 2 factorial is 2. 2 times 1. So that's 2 times 2 times 2 is 8. So I take 12 factorial and I divide by 8. So there's 59,875,200. Okay. You know the one about Mississippi, right? How many ways can you respell Mississippi? Well, Mississippi. There's Mississippi. It's 11 factorial, but you got 4 s's, so 4 factorial. You got 3 i's. 3 i's, so you divide 3 factorial, and then 2 p's, so 2 factorial. And so it becomes a lot less than the total. So anyway, you get the idea if you come up with one of those. And then number 23, corporation must appoint a president, chief executive officer, chief operating officer, and a chief financial officer. It must also appoint a planning committee with 4 different members. There's 11 qualified candidates, and officers can also serve on the committee. So to be appointed, there's 11 pick for, because once you pick the president, that's an order. You just can't pick 4 people to serve as the financial officers. You can pick 4 people to be qualified in the committee. So it's 11 pick for. So there's 7,920 ways to select the 4 officers, and the committee, there's 11 choose for. There's 330 ways to form the committee. That's the difference. Because the officers require order, the committee doesn't. It's just a group.
Yeah.
But this is a good problem to show you the difference between. What's the probability of randomly selecting the committee members and getting the 4 youngest qualified candidates? That's the trick question again. It's just 1 divided by 330. Once again, there's only one group that's going to have the 4 youngest. We've done that a couple times, so whenever you have a special thing like that, you can figure that out pretty easily. 25. When 7 basketball players are about to have a free throw competition, they often draw names out of a hat to randomly select the order in which they shoot. What's the probability that they shoot free throws in alphabetical order? Assume each player has a different name. If you put them in alphabetical order, how many ways there are to do that?
1 way.
There's only 1 way to put them in alphabetical order.
Yeah.
But how many ways can they choose to shoot? That's 11. It's ordered, so it's 11. It's 11 or is that 7? It's 7 tick. Seven. 5,040. You're using all of them, so, there's only one way to do that out of 5,040, so it's fraction 1 tab 5040. 7 factorial. That's the same way as saying 7 tick 7. Right? Because, see, that's the case where you would have, for this one, you'd have 7 factorial over 7 minus 7, which is 0 factorial. So it's 7 factorial over 1. So it's the same way as just putting 7 blanks up there and going 7 times 6 times 5, which is 7 factorial. All right, this is the last one. We're done. How many different ways can the word refer to your range? All right, so how many others? 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 factorial.
3 R's. So 3 R's.
So there's 3 R's and 3 E's. So that's 3 factorial times 3 factorial, which is 6 times 6. It's 36. 3 times 2 times 1 is 6. So 1120. You guys are quick. Quick study.
I got like 3 brain cells left.
All right, so you got fresh ammo for homework number 5. And we will meet Thursday. Thursday we're going to do, it's called, we're going to do random variables of discrete nature.
Okay.
And then next week we start continuous random variables. That's how we'll end up. At any rate, we're moving right along. Any questions?
None.
None. Turn me loose, he said.
Yeah.
Thanks for
Ring
coming.
that bell.
Thanks for coming. I don't think we'll be this late next time.
It's all fine.
Okay.
It's all
Be sure to email me or text me if you have questions, okay?
definitely will.
Thanks. Once again, it's fresh, right?
Yeah. Go home, eat, do it. Or
Okay.
the door system.